variable. So yes, I'm going to put this. Correct. What I meant to say is that this is also known as y, but since the independent variable uses y, let's not get it confused. Correct. But the function can be replaced by y at any point in time. Not in this case, since the independent variable is chosen to be y. Absolutely correct, yes. Thank you.
Did we figure out if the
Are you muted, or did I lose you, Colby? Hello?
hello?
Yes, Colby. Yes, we only heard the, or maybe I only heard the first part. Can you repeat the question?
Yes. Is how we find the direction of the derivative function and the regulated function, like if it's going down or negative up?
So for the
negative,
function,
positive?
I'm only looking at numbers. If the function here is 0 and then it's -1, obviously it's decreasing. If the function is negative and then at some point in time is positive, between these two, it must have been increasing. From 1/3 to 0, it must be decreasing. From -1 to 1/3, it must be increasing.
Okay, I see now. The zeros we found out.
The zeros are for the derivative.
I was talking about the zeros on the infinity and negative infinity.
Oh, these are determined by the limits, and why? Because why I wanted to determine them? Because I want you to see that from 0 to -1, the function is decreasing, and that's what the derivative says. But this is not an actual point. -infinity comma 0 is not an actual point. It's where the tendency is. The function approaches 0 as y approaches -infinity. But this is not a point. This is a point. This is a point, but this is not a point. A point cannot have infinity as any of the coordinates. Very good question. Is that okay?
Yes.
Okay. I would like to look at some other type of function. So this was a rational function. I should have asked you. But here's another type of function, and this is problem 63. That caught my eye. And this is f of x, x to negative, I lost it again, x to -2 times natural log x, and the interval is given to us as 1/2 comma 4. This is a totally different type of problem. Here we're asked to find absolute max min on a closed, so when we have brackets, we also call closed interval. Not on the entire domain. So here we were asked to find critical numbers, and if they change into max min. The domain was not restricted, so we looked at the entire domain. But here, the question is different. They're asking us to find absolute max, absolute min on a closed interval, and the closed interval is given to us. In that situation, I am restricted to this interval. I don't care where the function is defined, but I do know that my analysis has to be on the interval 1/2 4. That's what we are given. So, where is my starting point? What do I have to do first?
On the derivative?
Of course. So f prime of x, x to -2 prime is -2 times x to -3 and multiply by the natural log. It's a product, please, plus x to negative 2 times the second function prime, which is 1 over x. Okay. Negative 2 natural log x over x to the third plus 1 over x squared times 1 over x, which is 1 over x to the third. So this is negative 2 natural log x plus 1 over x to the third. I like it because I don't have to find the least common denominator. It's already done. It's the same denominator. Okay, and now we know that critical numbers come from two sources, and I have to, for any function, analyze both. What are the two sources?
Undefined and 0.
Good, undefined. So f prime of x is undefined when x equals 0. Excellent. I want to put in the table. It doesn't fit. No. Okay. The other option. It doesn't fit not just because of that, but also I can plug in 0 in natural log, because the function is undefined at 0. Okay, what is the other option?
F prime of x equals 0.
Good. When is the fraction 0?
When the numerator is 0.
Let's solve the equation. If I can turn the page, maybe I can. Good. So I have 2 natural log x equals 1, because I can move it to the other side, it doesn't matter. 2 natural log x equals 1. Obviously, we have to do what first here?
Divide by 2.
Very good. Natural log x equals 1/2. And remember, this is equivalent to, what is the base here? I don't see any base. What is the base of natural log?
E.
E raised to this power equals x. So e raised to 1/2 equals x, but e to 1/2 is the square root of e. Okay, in case you have any doubts about the square root of e, you just put it in, and you take the square root. Where's my square root? Of e. Simple plain e is right here with no power. So 1.65. It's the only 0 for the derivative. I have to plug this in, and I will plug it in as the square root of e in the function and get the y value. So back to the calculator, I will put in y equals this function, which is natural log x divided by x squared. Okay, so go to second and table, and I need, yes, I know, don't rush into calculations, Mr. Calculator, 0.5, which is the leftmost point. Then I have the square root of e, now the approximation, and I want 4. Okay, so let's see. I think 2 decimal digits would be enough. So negative 2.77, 0.18, and 0.09. Okay. Good. So now I will study the sign of the first derivative. Okay. So as you notice, between 1/2 and 4, this will be a waste of time because it can never be negative between 1/4 and 1/2 and 4. But if I go to the negative side, which I can because of natural log, but if I had negative values, then I cannot disregard this about the sign. I can disregard it now because it will be always positive. Okay. So you can say, how do I find the sign of this? Very simple. I will put in the calculator as the second function, and I have -2 natural log of x, close the parenthesis, plus 1. And I want to plug in a number to like 1/2, that's what I need, 0.5. And I want to plug in 4. I already have those numbers in there. So at 0.5 is positive, and at 4 is negative. That's all I needed. So it's positive, the derivative. We don't study the sign of the function, please. We only study the sign of the derivative. I plugged in 1/2 and it was positive. I plugged in 4 and it was negative. At this point, I want to make sure that these two rows work well together. If they don't, I'll say, oops, I have to go back to the drawing board. Let's see. From -2.77 to 0.18, what does the function do?
Increases.
Good. Is that supported by the sign of the derivative?
Yes.
Perfect. From 0.18 to 0.09, what does the function do?
Decreases.
Is that supported by the sign of the first derivative?
Yes.
Good. Which means this is not the graph of the function. I see this altitude as at -2.77. I see this altitude at 0.18. And I see this altitude at 0.09. And now I'm able to establish, what does 1/2 comma this represent? What does 1.65 comma this represent? And what does 4 comma this represent from my altitudes here? So what is the first point?
Nothing.
It's the end point, and it's the smallest of all.
Absolute min.
Absolute min. Excellent. What is this point?
Absolute and relative max.
Absolute and relative max. Brilliant. What is this point?
Nothing.
Nothing. Excellent. That's how we study a function on a closed interval. We find critical numbers. We study the sign of the derivative. And we plug in the function, the endpoints, and any critical number. If we have 1, 1. If we have more than 1, we have to all plug them in the function and determine these values. Then establish that these two rows work well together. That's where this is important, because then that's when I catch my mistakes. If this were reversed, then I'll say, wait a minute, something is wrong. Who knows? Trust me, I can make errors. But as long as these two work well together and I'm able to analyze and establish which one is what, then I'm in business. Any questions for me?
Yeah. The square root of e that we got for
Yes.
setting the derivative to 0.
Yes.
I got to the ln x equals 1/2, but I kind of got lost from there.
You mean here?
Yes.
Okay. So there is a very important property. Log base a of x is y is equivalent to a raised to y equals x. A raised to y equals x. This says that any log equation can be conversed or changed into an exponential equation, and vice versa. Any exponential equation can be changed into a log equation. So here I had natural log x equals 1/2, base raised to 1/2 equals x, base raised to 1/2 equals x. Based on this property, that any log equation can be converted into exponential, any exponential into log.
Okay, yeah, I get it. Thank you.
Thank you. Okay, I think we had enough of this. Moving on to 4.2. We're going to look at two theorems here. One theorem is called Rolle's theorem. So let's take a look. So this is an interval a comma b, and by construction here, you'll see f of a equals f of b. Similarly, I can have this situation. And I can continue forever. Okay, so these are two examples. They really mean the same thing. So let's discuss this theorem. Number one, based on the examples I gave, would you agree that f of x, so this is f of x in this case, of course, and this is f of x in the other case. F of x is continuous on the interval a comma b? Would
Yes.
you? Good. Would you agree that f of x is differentiable, at least on the open interval a comma b? We don't care if it's not differentiable at the endpoints. It can have a vertical tangent there. We don't care. So would you agree that the function is differentiable? It doesn't have gaps. It's continuous, right? It doesn't have corners. It doesn't have a vertical tangent. It doesn't have a cusp. So it's differentiable.
Yes.
Number three, would you agree by construction, it's very clear that f of a equals f of b?
Yes.
Since all these three conditions are fulfilled, then we will say by Rolle's theorem, and this will bring you wonderful memories, there exists a C in the open interval a comma b such that, so let's take a look. Such as what? So by Rolle's theorem, there exists at least, that is in mathematical terms signified by the exclamation point. So there exists at least one, more than one, at least one C in the open interval a comma b such that Such as what? What am I
Just a
showing?
minimum.
Such that?
Zero.
Exactly. In other words, if a function is continuous and differentiable, and it starts at the same point it ends, it must have a term, at least one. How can a continuous and differentiable function, so unless it's this, right, a line, a horizontal line, but how can a function be differentiable, continuous and differentiable, and started at one point and end at the same point on an interval if it doesn't have at least one term, one max or one minimum? It can have 10,000, but at least one. It has to have a term. So Rolle's theorem says if a function is continuous and differentiable, starts at the same point it ends at, there must be a value, at least one x value, that makes the derivative zero. In other words, it must have at least a max or a min. It has to turn.